In this video, we are going to continue our discussion of vectors in 3-space by applying it to some force problem. So a 500-pound load hangs from 4 cables of equal length that are anchored at points plus or minus 2, 0, 0, and 0, plus or minus 2, 0. The load is located at 0, 0, negative 4. Find the vectors describing the force on the cables due to the load. So we have that picture. I kind of went quick through that description because it's easier to see in the picture. We are trying to describe the vectors with the force of 500-pound load hanging with the dimensions that they gave us. So first off, let's go ahead and label. I'm going to call these vectors F1, F2, F3, and F4. Now, I can use the points here to describe the direction, but it doesn't take account for the load. So we are going to name every one of them with a scalar. So let's find the vector first. Leave some space right there. Well, let's go ahead and say that scalar is C1. That's going to be the force in this direction. Now, F1, remember, it's terminal point minus initial. So 0 minus 0. 0 minus negative 2 is 2. And negative 4 minus 0 is negative 4. So I have the force on F1, C1, being multiplied by the direction, the vector. Okay, so F2, I have a new force C2, whatever that's going to be, and I got to find F2 now. And now we're dealing with the terminal point here, or sorry, initial point here, terminal point there. So 0 minus 2 is negative 2. 0 minus 0 is 0, and negative 4 minus 0 is still negative 4. F3, right, now we're dealing with this point. You can name these any way you want. I just chose the way that I named them. I just whatever came to my brain. You can do it in any order, though. 0 minus negative 2. Okay, so we get a C3. That's the force. 0 minus negative 2 is 2. Then we get a 0 and a negative 4. F4 is C4. That's the force on there. And then we got this point now. So 0, negative 2, negative 4. And you can see we have like almost every alteration of the forces there given those numbers. It just kind of works out that way. All right. So I do want to point out a few things. The force that's going here is a down force of the force itself is we could actually call this 0, 0, negative 500. I know that it's going down for negative 500, which tells me the magnitude for that is 500. The force is pulling it down. We don't use negative 4 because that's just where it's at. The force itself, though, is what we have there. Okay, so notice that those points are distributed nice and symmetric. So due to symmetry, we know some things. Due to symmetry, we have the magnitude of F1 vector is equal to the magnitude of F2 vector, which is equal to magnitude of F3 vector, which is equal to the magnitude of F4 vector. The reason we know this is because if you look, they're all 2 points away from the origin. The weight would be evenly distributed from the 4. We also know that because the lengths are the same. Okay, so due to symmetry, we have that. We also know, we have one more thing from that. This, which implies that C1, the force on C1 is also to C2, which is also to C3, which is C4, and then we're going to call that C. Let's actually do that formally. Let C equal C1, C2, C3, C4. Sorry, my mathematician brain is not letting me not do that. So which implies that. So we're going to call that C. Also, we know that the resultant force, F, is going to be the sum of the forces that are holding it. Okay, so what does that mean for us? Well, I can actually add all my forces up now. Force is equal to, okay, I know all those are going to be C up there. So when I add them together, if you look, we're going to have, let's go ahead and rewrite this just to help. 2C negative 4C This is negative 2c, 0, negative 4c. This is 2c. We can change them all to c since of the symmetry. They're all the same weight. 0, negative 2c, negative 4c. So if I add all those up, notice I get 0, 0, negative 16c. Okay, well, I know what f is. We already described it. F is 0, 0, negative 500. So that's going to equal that, 0, 0, negative 16c. Notice we do get an equation out of here. Only the z component gives me anything. So if I do that, and I divide, I use my calculator, whatever you prefer. A lot of you guys could do it in your head. I'm going to be lazy. 125 over 4. Okay, so now all I got to go through and put c where it goes on each one of those, and I am done. So f1 is equal to 0, 125 over 2, and then those 4s are going to cancel, give me a negative 125. F2, you can see that these are all going to be the same. It's just that 125 over 2 is going to either be positive or negative, and it's going to move around. F3, so I got 125 over 2, 0, negative 125. All I'm doing is plugging this c up there. That's all I'm doing here. To find the actual each vector, each rope, this is the vector that would describe it. All right, that's all they ask for. Sometimes they'll ask for what is the vector of the resultant force, stuff like that. Obviously, we have that right away. These problems can be very, very helpful for your physics stuff. Physics, different types of problems in statics where things are just sitting still and the forces need to equal to 0, stuff like that. So vectors can be very, very useful in a very, this feels very primitive to me. Like it doesn't actually take a whole lot of math, even though the problem is longer. We really just did scalar vector multiplication, and we did vector addition. That's really all we did. No calculus, nothing involved.